Hi everyone, and thanks for joining us today. My name is Tomasz Stradomski. I'm senior staff data engineer at Ocado. I work in Ocado for 11 years, and I have over 15 years of experience working with data warehouses, big data systems, and in general, building data platforms. Today, I would like to tell you how we process the data in Ocado, and the second most important part will be about optimizations of our queries and tables in order to increase the performance and reduce the cost of using our big data systems. But before going into technical details, let me very quickly tell you who we are. So basically, Ocado has evolved from UK e-commerce startup to a global technology leader if it comes to running online grocery business. We offer a solution that we call OSP, Ocado Smart Platform. This is basically end-to-end solutions that combine software, hardware, robotics, different kind of advanced technologies, machine learning, artificial intelligence. And we have a pleasure to work with 13 partners all over the world. At the moment, our Ocado team in technology contains 2,000 people, including engineering, product, data science, and UX. We have 10 development centers in 8 countries, and we filed more than 1,200 of patents. On this slide, you can see some of our partners, or all of them. As you can see, we work, for example, with Kroger in US, Coles in Australia, and also we have a partnership here in Poland. We cooperate with Auchan. As you can imagine, taking into consideration the scale of our business, we collect petabytes of data. That's why it's extremely important for us to properly structure the data and optimize it. So what we are going to talk about today, we'll start with very quick overview how we process the data in Ocado. Then I will give very short introduction to BigQuery because this is our main tool. And we'll start discussion about optimization. We'll start with table partitioning. Probably you have heard about that. Probably you are using it, maybe even every day. We'll talk also about clustering, about one ugly side effect of using a lot of partition tables, which is a problem with partition pruning, and how we solve it in Ocado. And the final part will be BigQuery specific, because first 3 partitioning, clustering, and tabled functions are pretty generic. You can use those methods in multiple databases, but the last part is BigQuery specific. We'll talk about Google Autoscaler for BigQuery and how we improve it by providing our own autoscaler for Google Autoscaler. Okay, so let's start the technical part. In general, in Ocado, we follow event sourcing approach. So basically, our applications are responsible for sending the data they generate in form of events to Kinesis stream in AWS cloud. So for example, when there is a new order in our system, there is an event sent. When the order is delivered, there is an event. When the order is picked, there is delivered. Payment taken, the event is delivered. From there, we have application. This is data flow application, which is responsible for reading the data from all the streams and loading it in nearly real time into BigQuery. We use BigQuery Write API, so we collect all our data in nearly real time. BigQuery is one of places we send the data. Second one is PubSub, because we also have some real-time processing in some areas. So we also stream our data to PubSub, but the BigQuery is the most important part here. As I mentioned, we work with multiple partners all over the world. And because of some legal constraints, some local rules, we, in most cases, follow single tenant approach. So basically, for every single partner, we have separate environment, BigQuery environment, and the data is located close to our partner. So, for example, for Kroger, we have BigQuery instance in US, for Morrisons and Ocado in Europe, and for Coles in Australia. So this is the place where we run most of our operations, our reporting, machine learning, etc. But sometimes we need to run some cross-retailer analysis. And in this case, we need to collocate all the data that we need in a single region. And we have a project, BigQuery, also, that we call the Research and Insight. And we basically copy not everything, but quite a lot of our data into Research and Insight to have the collocation in Europe. That's because BigQuery does not allow you to query the data from multiple regions in a single execution. And from there, we have a project that is created by our data engineers, data warehouse with a kind of data marts. This is like pre-transformed data that is very helpful for data analysts. Here we use dbt to manage all the transformations. So in our production projects, quite a lot of things is done by our software engineers. They, as data producers, are responsible for processing of the data, not only generation of the data, but also some kind of processing of the data. And data warehouse is fully managed by data engineers. As you have heard, we use BigQuery quite a lot. So just several important information about BigQuery. Not sure if you had a chance to work with BigQuery before, but this is just cloud-oriented database with SQL access, columnar storage, and it follows asynchronous massive parallel processing paradigm, which basically means that your query is executed on sometimes even hundreds of nodes at the same time in parallel. You can load the data in batch mode, or you can stream the data using streaming API or write API. You pay for usage. There are two pricing modes. First is called on demand. In this case, you pay for the volume of the data that is being scanned by your queries. At the moment, it's $6.25 per terabyte of the data being scanned. And second, capacity pricing, where you just pay for the performance. So you buy so-called slots, performance units in BigQuery, and you can use them however you want. In addition, you need to pay for storage. Good thing is that you pay for logical storage, so after compression. What is nice is that BigQuery is fully serverless and managed by Google. You don't care about clusters, scaling, etc., etc. It's serverless solution. You just submit your query to be executed, and you wait for the result. BigQuery does not support indexes like most modern databases and data warehouses, but it supports different optimizations techniques like partitioning and clustering, and we will focus on those things now. So let's start with table partitioning. The concept is very simple. Let's imagine that you have a table. Of course, this is just a sample of the data, but you have a table. Without indexes or any other method how to optimize I/O operations on your table, with every single query you need to execute full table scan. So your table may be even terabytes of the data. But partitioning allows you to split the data into separate subtables that are called partitions. So you choose partitioning column, and all the records with the same value in this partitioning column will be stored in one partition. So like in this example, we partition the data on date. This is daily partitioning. So for each day, we have separate partitions with records that corresponds to particular day. Real-life example, one of our tables with some information about orders. Full table scan is 766 gigabytes of the data. So if you scan it, you need to pay for it. But with partitioning applied, If you are interested in only single partition, you reduce the volume of the data to 420 megabytes. So from gigabytes to megabytes. So if you are running some daily reporting, etc., it's always worth it to partition the data. It's very simple. This is all you need to know. You partition the data on one column and that's all. Recommendation, just do it. In Ocado, we apply partitioning almost everywhere for consistency. In theory, Google recommends to do it for a little bit bigger table. Each partition size should be at least 10 gigabytes, but we don't care. We partition also small tables. In theory, the metadata management is more problematic in this case. So basically, database optimizer needs to scan more data to calculate the proper execution plan of your query, but we didn't observe any negative performance impact. So we partition everything, even small tables, for consistency. Our users used to know that the tables are just partitioned. We use daily partitioning in 99% of cases. In some areas, we have also hourly partitioning. In general, BigQuery supports monthly, daily, and hourly partitioning. Of course, partitioning is a general feature. It's available in other databases or big data systems too. One thing you need to consider is cardinality, so number of unique values in your column, because, for example, BigQuery supports up to 10,000 partitions. There are always some limitations. If it comes to partitioning, of course, it depends on the database. Some databases support partitioning on multiple columns, for example, Hive, but this is not the case in BigQuery. They support only partitioning on a single column. Of course, datetime or timestamp columns are not only columns that you can partition the data on. You can use strings, you can use integers. In this case, you need to define ranges for your data, and you can optimize your tables that way. Second thing I would like to mention today is table clustering. So I have a very quick question to you. Who has used table clustering before? Okay, thank you. So we will cover some theory, and then I will tell you how we do things in Ocado. So let's imagine that you have a table. In this case, just several columns, some identifier, and foo. This is the column that we use quite often in our queries. We restrict the data on this column very often. Of course, there are also some other columns, but at the moment we are not interested in them. In theory, we can partition the data on this column, but let's say that we already applied daily partitioning. And in BigQuery, we cannot partition on second column. What is more, the number of unique values may be huge in this column. In this case, partitioning is not very optimal unless on your own you define the ranges. And this may cause data skew. Some of the partitions may be much bigger than others. So let's apply table clustering. Table clustering is a little bit similar to clustered indexes. So the idea is to order the data in lexicographical order. It's natural ordering on the column that you cluster the data on. In this case, as you can see, the data is ordered on foo column. Then we can split the whole table into logical clusters. Most databases manage those clusters on their own by default. The size of the cluster in BigQuery is determined automatically. I would say that in most cases this is 64 megabytes, but they do it automatically. You just define the column you would like to cluster your data on. And in normal indexes or cluster indexes, database, when you search for some data with restrictions, would apply some search algorithm, etc., etc. Here, the case is different. In case of table clustering, we are going to store some metadata about each cluster. And the most important values are minimum and maximum value in each cluster. Now let's say that we have query with very simple restriction. So we are interested in those records with value in foo column equals 3. So now we can analyze our cluster. By we I mean BigQuery or any other database. So we can compare our restrictions with min and max. So let's take a look on the first cluster. We have values between 1 and 4, and number 3 fits somewhere between those values. So we know that our data may be located in this cluster. Let's take a look on second cluster. Min 9, foo 13. In this case, there is exactly 0 chance that number 3 will fit between those values. And the same for the third cluster. So in this case, BigQuery or any other database is aware that only one cluster needs to be scanned. So partitioning and indexes tells you where your data is located. Clustering tells you where your data is not located. We know that it's not located in green cluster, and we know it's not located in yellow cluster. Let's take a look on second example. We are interested in records with foo higher or equal 4 and lower or equal 13. Again, we need to scan blue cluster because of number 4 and green cluster, but we can skip yellow. From metadata we know that our data is not located there, for sure. Another example, only one cluster needs to be scanned. Of course, if the restriction is wild enough, you need to scan all the clusters. This is a very simple example, but we are talking about hundreds of thousands of clusters, and you can improve the performance, or in case BigQuery reduce a cost a lot using table clustering. This is best effort. So it's not like with partitioning or indexes. It's best effort. So they not guarantee perfect performance for that. That's because how data loads are managed. So let's imagine that you have two clusters, green and blue, and now you loaded the data into your table. It can be hundreds of megabytes. So resorting immediately the whole table may be very expensive. You may have peak hours for your data warehouse or something like this. So in most cases, the data that you are going to append, only this part, is going to be sorted, but only in scope of this batch load, or not sorted at all. In this case, 2/3 of your table is perfectly sorted, and 1/3 maybe. But there is a process called reclustering that at some point will groom your table again to make sure it's perfectly ordered. What happens in case of queries? Let's say that we have a very simple query with restriction of foo column equal 1. First table, we need to scan green cluster, we need to scan blue cluster, and we need to scan the new part. Because in every single cluster, there may be value equal to 1, recorded with this value. We know that from min and max. So we need to scan all 3 clusters. After reclustering, we need to scan only 2 clusters. Only A and B, because in C, we have only records with value 2. And we will see it in min and max for this cluster. How it works in different databases, it depends. Sometimes you need to schedule refreshes, sometimes they are done automatically. Google claims that they recluster tables automatically. They don't guarantee what will happen with the most recent load, but at some point they will recluster your table. It's automatic, it shouldn't have any effect on your query capacity or performance. You don't pay for it. But how does it work with streaming inserts? As mentioned before, we stream everything. So we don't use batch loss almost at all, we stream everything. So we've been interested how this automatic real-time reclustering will work in our scenarios. So we run following test. We have two tables, one is clustered and second is not clustered. And we are constantly streaming the data in micro batches, 10 megabytes per each request. And during the test, it took several hours, we stream 52 gigabytes of the data to each table. Cluster table is clustered on a column with 5 distinct values, only 5, low cardinality, and the data inside this clustering column is distributed equally. Every 10 minutes, we run a simple query. We are interested in everything in this table with particular state of the data. So again, 5 values. And we are interested only in more or less 20% of our data. So as you can see on this graph, the green upper line, this is the data being scanned by each execution of the query every 10 minutes. And the blue bottom line is the same, but for a clustered table. So as you can see at the very beginning, it's almost the same. For not clustered tables, it's constantly growing. And we see that reclustering appears at some point. When we load more data, then again, reclustering appears. And like this till the very end. After the test, reading the data from cluster table for only one value reduces the volume of the data being scanned by 80%. Our observation is that Google reclusters the data for every 4.5 gigabytes. So this is perfectly fine for us. We have quite a lot of tables that are being streamed all the time and they are clustered. What about clustering on multiple fields? It is possible, but the order of column is important. The first column takes the precedence. First table, not clustered at all. Second table, clustered only on one column, on country. So for example, if I'm interested in the data from US, I run a query where country equals US, and BigQuery will scan only one cluster. But what if I have a lot of queries that uses for restrictions not only country, but also status, or a lot of aggregations? I aggregate the data on country and status. I can further optimize my clustering by providing secondary clustering on status, and BigQuery will create a kind of subclusters. So in this case, if I'm interested in the data from US, but orders only in processing state, BigQuery will at first find the US cluster and then this one particular subcluster. So in this case, I've optimized my table even more. So you can do this, but it's important to design the order of fields carefully. To sum up, partitioning, clustering, you can use both techniques at the same time. This is what we are doing. You cluster your data on date, partition your data on date, and then you cluster on some other fields. It depends on your query. You need to analyze it yourself. And most databases, including BigQuery, will manage clusters within partition, for each partition separately. So to sum up, we partition everything. We try to cluster almost everything. We are in process of migration to cluster tables. And it works perfectly fine for the data that is being streamed in nearly real time. Is it more or less clear till now? Perfect, thank you. As I mentioned before, there is one ugly side effect of using partition tables a lot. It's called problem with partition pruning. You have a lot of tables that are partitioned, you have complex queries, and in theory, the query should scan only some of the partitions, but because of any reason, it's scanning everything. So database is not able to determine which partitions should be scanned and which not. Because you have a lot of joins, because maybe you have some mistakes in your SQLs, you forget to add something to your query, things like this. And this is especially painful when you are working with views, and we have a lot of views in Ocado. Very simple example. This query just deduplicates the data. I didn't mention that before, but in our data intelligence platform, we support at least one semantic, which basically means that every single event can be delivered more than once. So we need to deduplicate our data in BigQuery using SQL. So this is a generic approach. We are using raw number analytical functions to order the data, to find a raw number for each group, partition by some deduplication key. In most cases, this is primary key of your data. And we expose partition time column. This is the column that we use for partitioning, SPT. So the end user can decide which partition of the data they want to scan, like this. And it works perfectly fine. So the end user dynamically specify value for PT, which is just alias for partition time column, which is used for partitioning our data. So this will work perfectly fine, very simple example. But what if you have joins? For example, 3 tables. You will expose partition time column from first table, in this case table A, and the user can query it the same way. They are interested in data from particular day. But in this case, it will properly do partition pruning only for table A. So we need to add some criteria to our joining criteria to make sure that the optimizer of BigQuery and probably any other database is aware that we are interested only in this data from this particular day. This is how BigQuery is able to push the filter to very top. But what if you don't have collocation in this data? Let me come back to this slide. It may happen that you need to scan more than one day for some particular table. Let's imagine the situations that we have orders and deliveries, and the delivery may happen within 2 weeks after the order has been completed. Let's say this is artificial example, but let's say we have such a situation. In this case, we are probably interested in scanning more than one partition or delivery data or order data, for example, 2 weeks. It's very hard to achieve it in SQL in views. In theory, you can expose partitioning time column for every single table. But then you will have such a nightmare. So basically, you push a lot of knowledge to end user. End user must be aware that they need to scan one partition for table A, join it with 2 weeks of data or table B and 1 day of data in table C. And this is a kind of nightmare. And there is no perfect solution for that in views, but we have so-called table-valued functions. Table-valued functions is just the user-defined function that returns a table. So you can use it in your SQL queries in every single place that you would normally use a table or a view. But you have parameters, something that is not supported in views, at least not in standard SQL, which basically means that instead of exposing all those partition times, you can expose some parameters, in most cases just 2, start date and end date. And you can use those parameters to restrict the data on early stage of processing. So in the place where you select the data from your row table. So you don't care what optimizer will do with that. You enforce that optimizer is going to scan only the partitions between PT start and PT end. You can manipulate the values by using some datetime functions, for example, date subtract. So for example, for one table, you can scan the data between PT start and PT end. For other table, you can subtract 7 days from PT start to extend the date range that you would like to scan. A real-life example. This is one of our views. A single execution will scan more or less 90 gigabytes of the data. In this case, it's very hard to optimize it because of complexity of the query itself. Several tables are being joined together, etc., etc. But after the cost of this query is more or less $0.50 for every single execution. But after replacing with user-defined function, with table function, we reduce the volume of the data being scanned to 4.5 gigabytes and reduce the cost to $0.028. And we can optimize quite a lot of views like this. Is it more or less clear? Great, thank you. The last part. This is BigQuery oriented. So it's not all the techniques I mentioned before are supported by other databases, or at least some of those techniques. But this is BigQuery oriented. As I mentioned before, we have 2 pricing models. One is on demand, where we pay for the volume of the data that is being scanned. And second one is capacity pricing. We pay for the performance. So basically, you just choose how many slots you need and you pay for it. But you may have some peak hours, off-peak hours in your database, etc. Maybe you don't need that many slots all the time. So Google offered something that they called BigQuery autoscaler. And in theory, you just set the maximum value, how far BigQuery autoscaler can scale your configuration. In this example, the upper dot line just indicates that we can scale up to 2,000 slots. The red line shows the autoscaler behavior. The blue line shows our real demand. And as you can see, there is a lot of white space between those lines. BigQuery autoscaler is very aggressive. And let's take a look on the problem in a little bit different view. Again, a red line, autoscaler, blue, bars real usage. As you can see, we cannot reduce heavily number of slots because we have busy hours. We need performance between 4 and 6 a.m., maybe even 3. And we would like to rely on auto-scaling behavior. But as you can see, even, I would say, medium or even low demand on slots causes scaling up to the roof. And also the cooldown period is quite long. So after it has been scaled to the roof, it takes time to reduce. And the thing is that you pay not for the slots that you are using, but for the slots that are assigned by autoscaler. So in our use cases, we measure the efficiency of BigQuery autoscaler, and for us it's about 55 to 60%. So we are paying 100% and we are using only 60% of capacity. And this is the problem, which we solved by creating our own autoscaler for BigQuery autoscaler. The idea was very simple. So let's try to reconfigure the maximum number of slots in nearly real time. So we analyze windows, time, minute each, and we take into consideration some parameters like previous time slice slot usage, the number of pending jobs in the queue, and contention issues, which just indicates number of errors because of lack of resources. So we analyze it for the last 1 minute window, and then we decide if we can upscale, downscale, or leave the configuration as it is. So this is not predictive. We are not trying to predict. This is reactive. We analyze what is going on at the moment, and after maximum 1 minute, we may increase our configuration. This is good for batch-oriented projects. It's not good for ad hoc analysis because this 1 minute window, and for 1 minute you may see problems with performance. After that, we will rescale autoscaler, and it should work perfectly fine. So this is just our result on one of the projects. So the bottom green line shows the cost. This is the cost for the project managed by our autoscaler, and the blue line is theoretical on-demand cost. We can calculate it because we have detailed statistics of our queries. That includes the volume of the data that is being scanned. So in this case, we can calculate theoretical cost if we were on demand mode. And in this example, on demand would cost us, in this project, more than $12,000, but our capacity pricing with our autoscaler cost $3,000. So in this case, for 1 month, we reduced the cost by 75%. This is pretty cool result. It doesn't work that way all the time, but in general, we observe after several months that we have more or less 90% efficiency. We are consuming 90% slots that are assigned by 2 autoscalers. And we, in 22 BigQuery projects, at the moment we reduce the cost by 40%, comparing to on-demand, taking into consideration that there is this one drawback, which is 1 minute window when the performance may be not enough. That's why it's not good for ad hoc reporting, etc., etc. Okay, let me just very quickly sum up. So we've been talking about table partitioning, that you can partition almost everything, at least in BigQuery. Then we discussed table clustering of the data that is streamed to the table, clustering on multiple fields, and of course combining partitioning and clustering together, which is the best approach. We also discussed the problem with partition pruning, how you can solve it using tabled functions by replacing views if you are using views by table functions. And the last part was about BigQuery specific thing, which is autoscaler for BigQuery, autoscaler in capacity pricing mode. Yep, so that's more or less everything I wanted to tell you today. I hope you enjoyed it. I hope that you have learned at least one new thing today here in our Ocado office. And now I'm open for questions.
I was about to say we have time for more or less 2 questions, and I can see 2 hands in the air, so.
I have a question about, 2 questions. One is about the baseline. So do we have a baseline like how Databricks were doing, or Snowflake, let's say, so we can compare this BigQuery performance with that baseline? That's one. And in the second one, in the cost saving, it is like when you miss, like you said, it is reactive, right? So, but we have to be more like proactive to kind of like lease the resources before it is being used. So we have a lead time and this proactiveness. So we are losing 2 things, right? And in a time critical, let's say it's an ad tech, and where we are betting, so it's very important. I lose this time, so the business will lose a lot of money.
So let me answer second question at first. So for business critical queries, let's leave on demand because it can scale really well. You pay for the volume of the data being scanned, but you have performance all the time. So we have capacity pricing with our own autoscaler only for batch-oriented workflows.
No time criticality.
No. If you have like business critical reporting and you need answer within seconds, and no, let's leave on demand or autoscaler with a normal BigQuery autoscaler, but it may be more expensive than on demand in this case. Correct. You need to just measure it. About the first question, it all depends. We don't have the performance comparison between BigQuery and other databases. We compared it years ago when we chose BigQuery, like 11 years ago. It was the fastest one by far. We from time to time compare it with some other offerings like Athena in AWS. In most cases, BigQuery is much faster, but Athena is cheaper.
Okay, so let's have one more question. I think there was one hand here.
First of all, thank you for your talk. I really enjoyed your explanations. And might be I'm misunderstanding something, but can you clarify one slide? The one when you show the clustering based on multiple columns.
Okay.
Yeah.
Yes.
And the red section, shouldn't the rows be in reverse order?
Sorry, once again?
Because status, we see status.
Yes.
And the first row in the red section is cancelled.
Yes.
But also the cancelled row in blue.
Yes, because this is like ordering within the cluster. This is how you order the data by, for example, 2 columns. If you select everything from table, order by first column, second column. The first ordering is more important than second ordering is applied within the group.
Okay, thank you.
Yep. That's why it is important.
Okay, thank you for your questions. I think Tomek is going to be available for some time during the break, a 10-minute break that we are going to do right now, and also after the meetup for some time, right? So after the formal part.
Exactly. Thank you.